we are going to discuss our lecture on advanced reaction engineering. So, in this course we discuss about the effect of pressure drop in packed bed reactor. So, on this already we have discussed in our previous class. So, we have derived the differential equations, design equations for the pressures in a packed bed reactor. So, how that is affect with the weight of the catalyst, that already we have discussed, and we have derived the design equations for that packed bed reactors. So, now today we will discuss about the analytical solutions of that particular design equation when there is a reaction. So, in presence of reactions means when we are conducting the reactions inside of the reactor in presence of the catalyst. So, then so what would be the pressure drops. So, that part we will basically discuss. So, analytical solution for reactions with pressure drop. So, here is the our packed bed reactor that already we have discussed. This is our packed bed reactor. So, here in this particular systems, for examples, if you take a second order reactions, let us say A is going to B and the reaction is the isothermal reactions and second order reactions. So, in that case step by step means how we will derive the design equations and we will calculate the effect of pressures with increasing weight of the catalyst inside of the bed. So, that we will discuss. So, at the beginning, so this is our reactions, it is the second order reactions. In the step 1 what we will do, so this is the mole balance equation or the design equation for the packed bed reactor. So, this is the design equations F A naught into dx by d w equals to minus R A prime, that is the rate of the reactions for component A. So, the rate law, that also we know, that is the second order reaction, this is our rate law. So, that is the step 2. So, that rate whatever we will get, that will substitute in the design equations. Okay. So, now step 3, that is the concentration as a function of conversions, that we know for that particular reaction, that already we have discussed in our previous class too, how concentrations means molar flow rates, volumetric flow rates, that would changes with the temperature and pressures, that already we have discussed in our previous class. This is the volumetric flow rate as a function of pressure and temperature, how they are changing, and fractional volume change also. So, that part we will discuss. So, now if we consider a isothermal reaction condition, concentration we can express in terms of F A by small v, that is the volumetric flow rate. So, after that if we can express this in terms of C A naught 1 minus x into y. So, here y is the pressure ratio, that is the P by P naught, and x is the conversion, C A naught is the initial concentration of the reactants. Okay. So, now we have these equations, this is from the stoichiometry, the concentrations and conversions and pressure drops. So, the how they are related. So, this part we have basically substituted. So, now also we have derived these equations also from the Argan equations, we have derived these equations y equals to 1 minus alpha w to the power half. So, that we can substitute here. Okay. So, once we substitute the concentrations, initial concentration 1 minus x into 1 minus alpha w to the power half. So, this concentration terms in terms of this we will get. So, now we can substitute this in equation or step 1 here in the design equations we can substitute. So, the concentrations that we are substituting there. So, then in step 4 what we are getting. So, this equation in the design equation of the packed bed reactor. So, there is F A naught into dx by dw equals to minus R A primes, there we are substituting these red equations, there C A k into C A square is there, C A that we are substituting from here from the stoichiometry in terms of this. So, then the final equations is getting after rearranging we can get, if we rearrange these equations or integrate with respect to the x equal to 0, weight of the catalyst, that W equals to 0, then conversions x equal to 0, and when a W equals to W means W amount of the catalyst that would be placed inside of the reactor, then the conversions would be x. So, with that if we integrate after rearranging these equations. So, this equation we are rearranging, after that if we integrate with respect to these boundary conditions, when x equal to 0, weight catalyst weight equals to 0, when catalyst weight equals to W, then conversion is would be for that particular reaction stage X. So, after integrating, so we will get this. Okay. So, and rearrange, if we rearrange these equations, so then we will get X equals to this. Okay. So, this is the step by step procedure to how to get conversions for a particular reaction when there is a pressure drop in a packed bed reactors that we are conducting. So, here in the left hand side conversion is there, only conversion, this is the analytical solution. So, in the right hand side you can notice. So, here's brackets alpha into W is there. So, if you know alpha and weight of the catalyst W, so if we change the W, that is the weight of the catalyst. So, then if you know these are the parameters, means reaction rate constant, initial concentrations, weight of the catalyst, volumetric flow rates, and these are the parameters if we put except W. So, weight of the catalyst that we can vary along the as our means W and X, if we vary 1 kg catalyst, 2 kg catalyst, 3 kg. So, by that way means rest of the parameters are constants or for a fixed for that particular system. If we put alpha and W value, so accordingly conversions of that reactors will change. So, these equations we can rearrange also by this way also. Okay. The same equations we are rearranging these equations, left hand side we are putting catalyst weight, right hand side we are putting conversions. So, if you know alpha value and other parameters, so by changing both the equation are the same, but we are expressing different format. Okay. So, now see here in this particular equations, here's two parameters is there, one is the alpha, another is the W. Okay. The product of this that you have to put inside of these equations here. Okay. So, here's this alpha if equals to let us say 0, okay, then pressure drop would be 0. If we put alpha equals to 0 here, so then there would be no pressure drop inside of the bed or inside of the reactors. If there is a pressure drop inside of the reactor, then alpha we have to put as alpha. Okay. So, then this equation actually indicates or expressing that when there is a pressure drop inside of the reactor. So, then how if we change alpha value here, see also here if we with the catalyst weight, if we change the alpha, so means alpha value of the alpha, if we change from alpha equals to 0 to any value alpha. So, then accordingly the pressure will change and pressure drop will vary, and then corresponding conversions of the systems or the bed or the reactors, packed bed reactors will vary. This product of this alpha and W, that always should be very very low value, less than 1 should be, otherwise means it would be here. If you see in this equation, it is 1 minus alpha into W by 2 is there. So, this product of this alpha into W, that always should be less than 1s. Okay. So, let us say if W equals to let us say 10 kg of the catalyst we are putting. So, if alpha equals to 0.037 let us say, so then product should be 0.37, that would be always less than 1. So, that also we have to keep in mind. So, means whenever we are going to put a particular value, so then always we look into that product is coming, or when you are doing the calculations we should keep in mind that product should be less than 1. Okay. So, now we have developed this equation for that particular reaction. So, now in your previous class also we have discussed that the particle size of the catalyst that we should place inside of the packed bed reactors, that would affect overall conversions rate, concentration as well as pressure drop of the systems. Okay. So, if we increase the catalyst size by a factor of 2, let us say initially we have a catalyst 2 centimeters, that is the diameter of the particle. If we increase the catalyst particle size, that is double, okay, 4 centimeters, and or if we decrease the catalyst particle size, that is 1 centimeters. If we decrease, then so what would happen? Either if we increase or decrease, so what would happen the pressure drop of the systems. So, that we will discuss. So, at the beginning, so when we have started for the pressure drop calculations for a packed bed reactor system, Then we have started with the argon equations. This is the equations. In these equations you can see in the right hand side there are two terms, term 1 and term 2 in that bracket, third bracket. Here the term 1, that is when the flow is laminar flow. So, means in a packed bed reactors, when the reactant is passing through that catalyst bed, then the reactants will convert it into the corresponding product and that will pass through that bed. Okay. So, here these two terms are there. So, here the reactant that may pass through that bed, either it is laminar flow or maybe turbulent flow, two possibilities are there. So, if it is, let us say laminar flow is there, so then this first term is dominated, okay, for smaller particles, and if it is turbulent flow is there, so then the second part would be the dominated, okay. Depending upon that, so if let us say we have increased the catalyst size by factor 2, means initially let us say 2 centimeter was the particle size that would be placed inside of the bed of the packed bed. So, if we increase into double, means 4 centimeter we are doing now. So, then particle size we are increasing. So, once particle size we are increasing or doubling, so then this part would be the dominated part. So, then this part we can eliminate or we can remove that part from that design equations, or this part is the beta 0, that is the pressure drop parameter. So, then the equations, this part if for turbulent flow this part would be dominated and this part we can neglect. Okay. So, then the pressure drop parameters, that is called beta pressure drop parameters, since this part we are neglecting, then this beta 0 would be become this g by rho 0 g c d p 1 minus phi by phi q into 1.75 into g. So, then the equations, the pressure drop parameters would be this. So, here one things you can see in the pressure drop parameters, beta 0, that is inversely proportional to the diameter of the particles or the catalyst particles that we have taken for our packed bed reactor. So, that is inversely proportional, means if we increase the diameter of the particles, so then these pressure drop parameters will decrease. Okay. So, means pressure drop parameters and alpha and beta, how they are related. Okay. So, this is pressure drop parameters. So, alpha and beta they are directly proportional. So, alpha directly proportional to beta 0. Okay. So, then we can say that if we change the particle size, means if we increase the catalyst particle size, alpha inversely they are related. How they are related? They are inversely proportional, particle diameter and alpha. So, means here the pressure drop equations you can see we have used here y equals to 1 minus alpha w to the power half. So, alpha is here. So, this means if we change the catalyst particle size, so then diameters, if we change the catalyst particles, then alpha will vary or alpha will change accordingly. So, this we can write. So, if two different diameter of particles you have taken, earlier one if let us say smaller diameter, if we increase the particle diameter is larger, then that if we placed inside of the bed and if we conduct the same reactions by changing the particle diameter, so then alpha 2 value will different. Okay. So, alpha 2 value will decrease. If particle diameter increase, then alpha 2 value will decrease. So, this is alpha 1, this is alpha 2. Okay. So, this is dp 2, particle size having larger diameter, here particle size is smaller diameters. Okay. So, this is the condition. So, under these conditions we are considering. So, what would happens in the conversions and other parameters, that this is the equations that we have discussed in our last class. So, here since we have doubling the catalyst particle size dp, so then alpha 2 value will decrease. So, here if we increase the catalyst particle diameter, then alpha 2 value, alpha value, that is the you can say that pressure drop parameter also, means with related to the beta 0. So, beta 0 and alpha that they are related like this. So, this is the pressure drop parameter I said. Okay. So, if you decrease the pressure drop parameter, so that implies that decrease the pressure drop, increase the conversions and increase the reactions rate. Okay. So, that would means if we increase the catalyst particle size or diameter of the particles, then what would happen, pressure drop will decrease, means pressure drop that will decrease, means inside of the bed the pressure gradually, means if we take smaller diameter particles, the pressure drop will be developed inside of the bed, as compared to that if we use larger diameter of the particles, then pressure drop will decrease. So, that would be our, whenever we are going to design, that always we expect that the pressure drop either should be 0 or some lower value than that. So, therefore, we can increase the particle diameter. Okay. So, but particle diameter once we increase, that is not always true, means up to what limits or what dimension or what diameters of particle size we can and select for a particular packed bed reactors. We cannot go for very smaller diameter particles, we have to increase the particle diameter. So, up to what extent we should increase, means any diameter we cannot set, very large diameter particles we cannot put or placed inside of the packed bed. So, that would overall affect the means that would decrease the pressure drop, that is good things, but at the same time overall conversion yield selectivity also will affect, that will discuss. Okay. So, if conversions is increase, means if we increase the catalyst particle diameter, then conversions will increase. This is not true for always. Okay. So, means we are considering here reactions with the pressure drop also, means when we are increasing the catalyst particle diameters, let us say this is our catalyst particle diameter, earlier was very small diameter particles. So, if we increase the catalyst particle diameters, so interparticle diffusions that we will discuss more details in later, but that interparticle diffusions part will affect, means reactant molecules, this is catalyst, let us say, that would diffused inside of the pores of the catalyst, and that would pass through that pores, and then that would interact with the active sites of the catalyst, then reactions will occur inside of the pores where so many active sites or active parts of that catalyst are there, active sites. So, there the reactants will interact and converted into desired products. So, if we increase the large particle size or particle diameter, so the interparticle diffusions that part would come, that would affect overall rate conversions. Okay. So, for large particle size it takes longer time for a given number of reactants as well as product molecules to diffuse in and diffuse out from the catalyst particles. Okay. So, whenever we conduct any reactions, reactant molecules will pass here and product will come out from that pore. Okay. So, therefore, for larger particle diameter, so that part means reactants it would takes longer times to diffuse inside of that particles or core of the particles. So, that would affect, therefore, we have to select an optimum particle size or catalyst particles, neither smaller neither larger diameter of particle. So, in between some particles diameters we have to choose, so which may eliminates the interparticle diffusions, at the same time pressure drop of the systems. Okay. So, here you can see, so here I said this is our particles larger diameter, this is smaller diameter. So, in case of this is reactants, after reactions product, this is the product. So, largest particle diameters, if we means change the particle size by increasing the diameter of the particles larger diameter instead of smaller diameter. So, then that would decrease the reactions rate, but at the same times means reactions rate is decreased, means it would take longer time to diffuse the reactants, and therefore, the specific reaction rate constant that will decrease, means how the reactions rate constant means for a particular reactions if you write minus R A equals to K into C A. So, here let us, it is first order reactions, here rate constant is this. So, if we increase the particle diameter, so then particle diameter if we increase, then reaction rate constant will decrease, means this part will drop or decrease if we increase the, then overall rate of the reactions will drop. So, therefore, a small particle diameter reaction rate constant is large and its maximum value will reach and the pressure drop is large in that case. So, smaller diameter particles reaction rate constant would be large and pressure drop would be large. Okay. So, therefore, we will get a low reactions, rate of reactions would be low. If it is a large particles, large size of particles, the pressure drop is small that is our expected, means therefore, we are increasing the particle size. So, then pressure drop would be smaller. So, but the reaction rate constant and reaction rate is small, therefore, the conversion should be low. So, but conversions means we are trying to decrease the pressure drop, but conversions at the means decreasing pressure drop, that is our expected, means that we are whenever we are going to design a reactor, packed bed reactors, always we expect that there should not be any pressure drop. Therefore, we are increasing the particle size, but at the same time we are losing conversions. Okay. Reactions conversions will drop. So, therefore, so what we have to do? We have to choose an optimum. Okay. See here this is the plot, if we means conversions x and particle diameters if we plot. So, then here you can see here what we are discussing, here reactions as well as pressure drops, means when we conduct any reactions inside of the reactor, when reactions will take place, then pressure drop how that would affect. Since if reactions, if we increase the particle diameters, that is the x axis we have placed. So, then the conversion gradually increase. Okay. If we increase the particle diameters, so here pressure drop dominates in this particular points, means up to this. Okay. So, but again if we further increase the particle diameters, what would happens, means up to this it is gradually increase, then the conversions will drop. If we go means from here to here, then the conversions will drop, means the lines will go this way this. So, up to this is the optimum particle diameters, up to this we can here pressure drop gradually will decrease, and here internal diffusion inside of the catalyst particle that will dominate, means further if we increase the larger size or particle diameter larger or bigger size, then internal diffusions will affect, means if it is smaller diameter of particles, then internal diffusion is very low or negligible. Once we increasing the particle diameter, diffusion part will dominate, and then that would affect overall rate of the reaction. So, neither very large particles, means if you want to drop the pressure drop, then larger particle is good, but there will get very low conversions. So, then we have to decrease the particle diameters. So, then if we go this way, so then here actually this is the optimum, means neither means that diameter of the particles would be more or much suitable to get maximum conversions. Here we will get maximum conversions. Okay. So, here also the pressure drop what that will come, that we have to accept, and that we have to design whenever we are going to design. So, neither very big particles of size of larger size of particles, or neither smaller diameter of the particles we should recommend. So, always we should expect that this should be the optimum diameter of the particles. So, where we can get maximum conversion for that particular reactions, and there the minimum pressure drop inside of the beds. Okay. So, the pressure drop in the packed bed reactor, that part is over. So, next day we will discuss about new things. Thank you. Okay.